Can you see my window?
Yes, sir.
Okay. It is in the full screen, na?
Huh.
Okay. Well, last lecture we were talking about the introduction to generalized linear model. Okay, can you see the caption simultaneously? So, why generalized linear model? Generalized linear model is a natural generalization of classical linear regression model. It is a generalized linear model. Why it is general? Because it talks about the family of distribution when the response follows as exponential family of distribution. It is generalizing the classical linear models with certain common properties like the estimation procedure and linearity property of classical linear regression models remain same in the generalized linear models. So generalized linear models is useful for the binary response, multinomial response, which you can say that categorical response, count data. Of course, the response having a normal distribution like quantitative data, response having a non-normal distribution like exponential and gamma. So we can apply the generalized linear models for all such cases on the line of a classical linear regression models. While applying the generalized linear models, we should remember the certain properties. So in generalized linear models, we talk about the two properties. One property is of variance is a function of mean. And second property is independentness, or you can say that the observations are uncorrelated. Errors are uncorrelated. So whenever the errors are uncorrelated and the variance is a function of mean, we can apply the concept of a generalized linear models. In the last lecture we discussed, we cannot use the generalized linear models when the errors or the data or the experiment is a kind of a split plot experiment where there are two errors are there and they are correlated with each other. So we cannot apply. Similar to classical linear regression models, in a generalized linear models also having a two part. One is a fixed effect part and second one is a random effect. So our basic idea is to get the maximum information about the fixed effect by minimizing the effect of the random part. And that is what in the second semester or in a classical linear models and regression analysis, we have used the concept of theory of least squares, where we have minimized the error sum of, or you can say the residual sum of squares, and obtain the best estimate of the parameters which are available in a systematic part to give the best prediction of the response. So, how to fit the generalized linear models? As I earlier discussed, that for a same data, you can apply the different approach. For a same data, you can develop a different models. But before applying the generalized linear models, we have to understand the nature of the data. So that is what the first step is saying, that the problem of looking at the data. So in that step, we have seen how the data are generated, which instrument is used to measure the data, what is the nature of the data, whether it is a qualitative data or quantitative data, and according to that, we can identify the appropriate model. Once we are very much clear about the data, we wish to see that is there any patterns in the data or not. So in last lecture we discussed about the pattern set. So here alpha and beta, these are the two quantities in the model y is equal to alpha plus beta x. Is explain the model completely. If you know the value of alpha and beta, given a value of x, you can exactly obtain the value of y. So in short, y and x are connected by this pair of alpha beta. So that means alpha and beta is try to get the patterns available in the data. So for a given a value of alpha and beta, if you make the changes, or if you take the different value of x like x1, x2 up to xn, then it takes the different value like y1, y2, yn, and that y1, y2, yn will be alpha plus beta x1 plus alpha plus beta x2, likewise alpha plus beta xn. It means that for a given a value of alpha and beta, we can reconstruct the values of y exactly from those of x, so that given x1, x2, xn, the pair alpha beta is an exact summary of y1, y2, yn. So that means if we know the alpha and beta, we can easily obtain the value of y1, y2, yn, and that is exactly. So instead of the observing, or if instead of doing the new experiment and observe the value of y, if we can try to identify the value of alpha and beta which is available based on the data, then perhaps we can minimize the cost of experiment and we can predict the value of y based on the given control situation x. But the thing is that, are we in that position to obtain the exact value of alpha and beta? Perhaps not. And that is how we try to identify, are we in that position to get the some value of alpha and beta, say a and b, which is some sense best describe the new approximate relation between y and x. Earlier we have the relation between y and x is exact. Of course, it is a linear. Why it is exact? Because you know the exact value of alpha and beta. But in real life, to know the exact value of alpha and beta, it is not possible. So what we say, are we in the position to obtain the best value of alpha and beta, say and b, so that the relation between y and x is approximately linear? And if we can, then given a value of x1, x2, xn, you can obtain the quantities a plus b x1, a plus b x2, and a plus b xn, which we denoted by y1 cap, y2 cap, yn cap. That is the fitted value of y1, y2, yn. And they represent a pattern set which approximate the data, and they can be summarized by the pair a and b. So whatever the information you can get, y1 cap, y2 cap up to yn cap based on the x1, x2, xn, that information can be summarized by the pair AB. So it is said to be a pattern set. So once the model is designed, first we say that we look at the data carefully. Is there any patterns between them or not? So that you define that there is a pattern, and that pattern is of a linear in nature. Now your basic idea is to obtain the best estimate value of alpha and beta. As in the second step, we said that let us say a and b is the some best value of alpha and beta in some sense, but in which sense? So that we will discuss in the step 3, that is the model fitting. We have identified the relation between y and x is a linear, but I wish to estimate the value of y based on the x. That means I wish to obtain the pair AB in a such a way that the pattern set yi cap is closest to yi. Because ultimately our aim is that yi cap is your predicted value, yi is the observed value. So when we say that yi cap is closest to yi, it means that the difference between yi cap and yi is almost negligible. So we can say that residual close to zero. How can we define the closest? Here the word is used that we have to obtain the estimate of a and b for the parameter alpha beta in such a way that yi cap is closest to the data yi. So now the question is, how can we define the closest? To do so requires certain assumptions to be made about the variation in the y that is not accounted for the model. In second semester, we had used the measure of discrepancy, that is nothing but the least square. And what is the least square error? Minimizing the least square error, it is nothing but the summation of yi minus yi cap square. That is summation ei square, and ei is equal to yi minus yi cap. So we call them as a measure of discrepancy. Discrepancy means it is a measure of difference. This formula has two implications. So if you look at this formula carefully, it has two implications. What is the first? The simple summation of individual terms yi minus yi cap square. So this formula has a simple summation, and it is a summation of the quantity yi minus yi cap square, each depending only on the one observation. So you can see that yi depends on the ith observation. If you take I equal to 1, it depends on the first observation likewise. That means this quantity is depends only on a one observation, implies that measurements are all made on a same physical scale and suggests that measurements are independent in some sense. It means this quantity is nothing but the sum of the square of the difference between observed and estimated value, and that square yi minus yi cap square, it is obtained based on a single observation. So by looking at this formula, we can say that we have used the same instrument to measure the data, and simultaneously that information is contributed into this particular sum of square. So it means that it is the sum of square of independent observation, and that is how we have the one of the assumption in the least square method is that residuals are independently distributed. So we have taken the assumption that the covariance between epsilon I and epsilon j is 0. That means epsilon I are independent. And what is the estimate of epsilon? It is a residual ei, and ei is here yi minus yi cap. So it satisfies our first assumption of independent. Secondly, the use of the function yi minus yi cap imply that even a deviation carries the same weight irrespective of the value of yi cap. So you can see that in a summation, each observation carries equal weight. You can see that there is nothing in the multiplication with yi minus yi cap square in the summation. So here the coefficient is, you can say that multiplication coefficient is 1. That means we can say that every term contribute the equal weight in this particular summation. So that is happening in the theory of least square, that the assumptions of the independence is there, and similarly it is saying that all the residual square having a equal weight. If we model variation in statistical term, then the first property of independence become the stochastic independence. If we talk about the statistics, then independence property is called the stochastic independence, and the second property is interpreted by requiring that variance of the distribution of the deviation be independent of mean. So when I am saying that the variance, or you can say that each quantity contribute the equal weight in the sum, that property is saying that the variance of the distribution of deviations. Deviation here is that yi minus yi cap. So if you find out the variance of yi minus yi cap, it is free from the mean. That means variance is a free from mean. Where when we talk about the classical theory of least squares. However, in our generalized linear models, we have a two assumption. One is independentness, that is stochastic independence, and second is a variance is a function of mean. So that is how it is different from classical theory of least squares. Anyway, we will discuss it again in later. So statistics are accustomed to go further and to build into their model and explicitly frequency distribution from the residual variation. So now we wish to identify. We are not just focusing here that whether they are independent or not, whether the variance of the distribution of deviation to be independent of mean or not, but we try to see that what is the distribution of the residuals, how the residuals are distributed. In classical theory of least squares, this was the normal distribution in which the frequency of y is given by this. So if we model the errors in a classical theory of least square, then we say that it is a normal distribution. Here it is a f of y is proportional to this quantity. When I am saying that proportional to that quantity, that means I have not taken the normalizing constant. In we know that in a regression, normal distribution, normalizing constant is a 1 of root 2 pi sigma. So here sigma is the standard deviation of the distribution and act as a scale factor. So it is a location and scale family. This is said to be mu is a location parameter and sigma is said to be a scale parameter. And here the scale parameter describing the width of the errors when above measured about the mean. So how far or how it is deviated from the mean observation. So that can be identified through the sigma. If you look at the function 1.1 in a two ways, if we regard it as a function of y for a given value of mean. So here if you look at this as a, it is a function of y given mu. That means mu is fixed and y is observed, then it is known as a probability density function. Alternatively, for a given value of y, suppose if we are saying that let us say y is fixed, and if we consider it is a distribution of a mu giving the relate, then it is talking about the concept of the likelihood function, and that is what given by the Professor R.A. Fisher. So when you say that it is the function of a mu given a value of y, then it is a likelihood function. And we know that how to write the likelihood function. It is the product of the density of a yi when yi follows the normal distribution. So here you can say that the L is proportional to the product ironing from 1 to n. And because it is talking about the proportional part, so we have not considered that root 2 pi sigma. So that is exponent of e raised to minus yi minus mu I square upon 2 sigma square. But we know that if we wish to obtain the estimate of the parameters, what we do? We take a likelihood of this particular likelihood function. So if we take the log of this likelihood function, what it say? It is a log L. We denote as a small l, and small l is nothing but it is a minus twice sigma square summation yi minus mu I square. And if you multiply it by the minus 2l, then minus 2l is proportional to this. This 2 will be cancelled out. So it is a 1 upon sigma square summation this. If you notice that the minus 2l for a simple n values, it is 1 upon sigma square summation ironing from 1 to n yi minus mu I square. That is apart from sigma square. Suppose if you will not consider the sigma square, then it is the sum of square, which is look like as the sum of square which we obtain in the model fitting, that is yi minus yi cap square. So it is a sum of square criterion. So now what is our basic idea in likelihood? We wish to maximize the likelihood function so that we can have the best value of the mu I, and that is called the mu I cap. So here it is the sum of the criterion. So what we do, we take the log likelihood, take the derivative and equate it to 0, and then find out the second derivative which is less than 0. Then we say that the mu I cap is nothing but the maximizing the value of mu I. But in our case, you can see that if you look at it, the sum of criterion, what we are looking for, that this yi. If you find out the expected value of yi, it is nothing but the mu I, because you can see that the yi follows the normal with mu I and sigma square. So it means that we wish the observed value which is closest to this mu I. So when you are looking for this closest to mu I, so it means that you wish to see that this difference or the sum of square of this difference should be minimum. So that is what the least square criteria is saying, that you are trying to find out the yi minus mu I. Mu I, instead of mu I, we have taken over that yi cap square, which should be minimum. If you take the derivative with respect to parameter equated to 0, then mu I is nothing but the y bar. You can try it home and you can get mu I equal to y bar. That is the arithmetic mean of y. For a more complex model, let us mu is varying from value to value, we define the closest set yi cap to be that whose values maximize the likelihood. So ultimately, we wish to find out the best value of mu I so that this likelihood should be maximized. So if we wish to maximize this, it means when you can say it is maximized, if you are maximizing this, that means minus 12 having the 12 having the sign minus. So if you have to minimize this particular minus 12, so minimum of minus is maximum. For a more complex model, okay, that is what we talked. So ultimately, to maximize the likelihood, it is equivalent to minimize the minus 12. More generally, we can regard not only that point that maximizes minus 12, but also to shape of the likelihood surface in the neighborhood of the minimum. So we wish to maximize among the neighborhood, because when we talk about the likelihood, it is talking about the information contained in the data, and that we wish to maximize. So it is in the form of, you can say that in the limiting case, you are trying to maximize the value in the neighborhood of minimum. This share tells us in the Fission terminology how much information there is about the parameters of the model in the data, as well as the best fitting values. So we wish to maximize in a such a way that how much this particular parameters contain the information of the y. So now they talk about that information should be extracted in a such a way that it should be the best for the model fitting. So now the question is that you talk about the how to look at the data, then you say that is there any pattern in the data, then you say that the model fitting. Now once the model is fitted, now you wish to see that whether this model is really good or not. So now the question is, what is a good model? To summarize, we aim in model fitting to replace our data y with a set of fitted value of y cap derived from the model. So to obtain this, what we do? When we say that the model is good, we say that the yi cap is very close to yi. Yi cap is nothing but that obtained based on the models. And if that estimated value of y is very close to y, we say that the model is good. These fitted values minimize the sum criterion such as the discrepancy measures. So we have to obtain the best value of y, say yi cap, such that it minimizes the some goodness of fit criterion. So what is that goodness of fit criterion? In classical theory of least square, it is a residual sum of square, or here it is a measure of discrepancy, and that is nothing but this quantity. We wish to minimize this quantity so that the yi cap is very close to y. So when you talk about the good models, what you feel at first sight, it might seem to think good model as one that fits the data very well. That is, that makes y cap very, very close to y. So when we say that the model is good, the first impression in our mind is that yi cap should be very close to y, and if you get the yi cap is very close to y, we say that whatever the models we obtain, that model is good. So if you remember in the second semester we study about the r square. It is a coefficient of determination, and what r square is suggesting, as higher the value of r square, you can say that the better the model. And how you can get the higher and higher value of r square? As you add more and more value of the x. That means if you give more information about the y based on the x, so that means as you increasing the x, the r square value is increasing. But now the question is that if you increase the r square, what happens? You can say that the model is good. How the r square is improved? You said, sir, we have added more and more variables. And if you add more and more variables, what happens? Model is good. But is this model is easy to interpret? No. Because more parameters, that means more variables, model becomes very complex. It is not easy to interpret. So what it's saying that at the first sight we feel that the y cap which is very close to y, if we can get this some kind of a model where yi cap is close to y, then we say that we got the best model. However, by including in enough parameters in our model, we can make the fit as close as we want. So if we add variable, more variables in the models, what happens? R square is increasing. We say that R square is near to 1. Our model is perfect. Fit is perfect. But what happens? That fit can always be reached to perfectness by adding more variables. In so doing, however, we have achieved no reduction in complexity produced. So by adding variable in the model, we can say that the complexity is not reduced. We have unnecessarily increased the complexity in the data or in the model. And whatever the models we are getting, it is a complex. It is no simple theoretical pattern to identify the data. The simplicity. So now we say that we need a best model, but the model should be simple to understand. Getting my point? We are looking for the model which should give the best value of the observation based on the models, or you can say that it should give the best prediction, but simultaneously we are looking that model should be easy to handle, easy to interpret. So what do you mean by the easy to interpret? What do you mean by the simple model? The simplicity represented by the parsimony of parameters. Meanness means it has some meaning. Is also a desirable feature of a model. When you say that the parsimony of the models, it means that it explains the data well and simultaneously it is easy to interpret. So when you say that parsimony of the model, it means that it is a balance between the complexity and explaining maximum information contained in the data. So we are looking for the model. We do not include parameters that we do not need. When I am saying that parsimony of the model, it means that we do not want to include the model which are not, or the parameters which are not desirable. Not only a parsimonious model available to analyst to think about his data, but one that is substantially correct gives the better prediction that includes unnecessary extra parameters. So when I am saying that the parsimonious model means it has the minimum number of parameters. When I am saying that minimum number of parameters means minimum number of variables in the model, and simultaneously it gives the better prediction compared to those models which are added unnecessary extra parameters, unnecessary extra variables. So some person can make a model with the 5 variables and R square is 90%. Some people are saying that I will add the only 3 variables and R square is 89%. Then which model is more preferable? Of course, the R square is 89%, 0.89, and having a 3 variable, because the variables are lesser, still it is giving the best information in the data contained. So an important property of a model is its scope. When you say that the model is a parsimonious, you have identified this based on the some goodness of fit criterion, identify the parsimonious models. But whatever the models you design or develop, it should have its scope. Its scope means range of condition over which it gives the good prediction. So it should not be that okay, whatever the models I have designed, it is good for this data. Then it has no meaning for the such modeling, because every time your data is changing. Are we in that position to use this model for a certain range of changes in the data point? If we can, then we can say that the model having a scope. What it's saying that scope is hard to formalize, but easy to recognize. And intuitively, it is clear that the scope and parsimony are in some extent related. So, whatever the models you are developing, parsimonious models, that model should having a scope. That means it should be used for a large range of the changes in the data point. Scope and parsimony are related to parameters invariance, that is parameters value that either do not change as some external condition changes or changes in a predictable way. Suppose you have changed the condition, then still it will help you to get the estimate of the parameters. It can be help you to predict the response. And suppose if you make the external change condition on a larger way, then the value of the predicted value is also changing in a predictable way. Everybody wish to be a straight modeler, but modeler is not the easy. Modeling is not the easy. Modeling in a science remains partly, at least, an art. So when you be a modeler, so you have to have your scientific wisdom as well as your intuition, your experience. When I'm saying art, art means it is within. It is your expertise, your domain specific knowledge. So modeling is a combination of the science and art. It is not the purely a science. It is not the purely of intuition and art. Some principles do exist, however, to guide the modeler. There are some principles are that we know that in the 12th standard we may have heard about there is a relation between the pressure and the time or temperature. As the temperature is increasing, the pressure is also increasing, and that is what the relation we have studied, that is called PV is equal to nRT. So P is proportional to time. Volume, that is V, is also proportional to the temperature, similar to the pressure. But pressure and volume are inversely proportional. Yes, as you increase the pressure, the volume is increasing up to the certain extent. So whenever you have the situation around you, you have to see that is there any scientific principle do exist? If yes, then we have to use that scientific principle. The first is that, so how as a modeler one has to work. So you have to Think like that. Let us, all models are wrong. Whatever models we have developed, none of them are the good. We try to find out the better one among the all the models. So whatever models we have, we try to identify which model is the better one among this set of the models. And the second principle, not to trust model exclusion of alternative. That is, as I say that you can have the same data, you can have a different model. If somebody is saying that no, no, sir, I had applied the linear regression analysis. Somebody said that I wish to apply the binary logistic. They can. So now you can say that how it is possible. When you apply the binary logistic regression and when you apply the uh, simple linear regression, that is not possible. Yes, it may be possible if you convert your response into the binary category. If your response is a binary in nature, then you can apply the binary logistic regression on the same data. So it is the modeler, how the modeler would like to see the data and what kind of the models they are making based on their requirement. Data will often point with almost equal emphasis at several possible models, and it is important that the analyst accept this. As I said that somebody is using the regression analysis, somebody said I wish to apply binary logistic. Let them, you have to accept. They have changed the scenario, they have changed the looking at the data in a different way. A third principle involves checking thoroughly the fit of a model and other quantities derived from the fit to look for the outlying observation and so on. So once the model is designed, you have to see that whatever the models is you have developed, whether it is really good fit or not. Is there any outlier present in your data or not? Such procedures are not yet fully formalized. So that imagination is required of the analyst here as well as in the ordinal choice of the model fit. It is not like that you can use the certain techniques and take the decision, oh, there is outlier present in your data. Here your art is required. Here your experience is required. Here your imagination is required. So that is how the modeling is a combination of a science as well as the art. First, as a science principles, you have to see that if some of the science principles do exist, we have to use, we have to capture their effect in the model. Simultaneously, we have to see that all the models are worst, but among the worst, which one is the better, that we have to identify. Same data we have, but we can look at the different models. This is the up to the analyst or the modeler, how he would like to see the data. Again, when I am saying that I wish to apply the binary logistic and somebody said I wish to apply the regression analysis, on the same data, they cannot apply both the models. But small changes in the data can allow you to apply the different method of predicting. That is, you have to convert your quantitative response into the qualitative and you can get the binary logistic regression. So there are mainly 4 steps over here. What is the first step? Anyone? What is the first step? The first step is look at the data carefully. Second step is identify is there any pattern. Third is
Model fitting.
model fitting. Very good. And fourth is
What is a
it?
good model?
So these are the mainly 4 steps of fitting of a model. Now we will see the how the generalized linear models arise. What is the origin of the generalized linear model? Data will be represented by the data matrix. We know that we have seen the general linear models where y is equal to x beta plus epsilon. So we have a x. X is called a data matrix. A data matrix will be represented by a data matrix, a two-dimensional array in which the rows are experimental or the survey units. For example, if you look at your Excel sheet, so you can have a row as well as the column. So rows are nothing but the cases. For example, name of the respondent. So name of the persons who have studied, or you can say that you can have a patient informations, you can have the surveyor informations. If you do the agriculture experiment, so you have a information on a different plots. So the rows are said to be cases and columns are considered to be a variables. So in a data matrix, it is the same. Rows are considered to be a cases and columns are considered to be a information on that cases. So in experimental or survey, the rows are plots in agricultural field trial, patients in medical survey, quadrants in ecological survey. Quadrant means in ecological survey you design the some square by some area in a some meter square, and that you are try to identify that how many birds are coming into that particular area, and based on that different quadrants you can say that how many birds are coming into the specific region, what is the different kind of a birds, what is the size of the birds, how many times the birds are there, at what time they are coming, in the morning or evening time they are coming, whether it is near to the river side or not. So something like that. You can have the such informations are that, but the area is your cases, and birds, type of birds, time of arrival of the birds. So these are said to be a column. And the columns are the varieties. For example, measurements, characters, treatments, grouping factors. So these are all said to be a column, whose values are believed to be affected by the other covariates, or they are affected by the independent variables. So now, what is the covariate? Covariate may be qualitative or quantitative. That is, taking a value, when I am saying it is a qualitative, it is a non-numeric, and if it is a quantitative, it is a numeric. We shall refer the qualitative covariate as the factor. We call them as a categorical variable, and that may include grouping factors, treatments, etc. And quantitative variable, independent variable which are quantitative in nature, we call them as a covariate. So that means if the variables are independent, it is classified into two parts: categorical or the qualitative, and quantitative. Qualitative independent variables we term as a factor, and quantitative covariate we term as a covariate. So these are the some notation which we are using. We know that y is a vector of observation. It is n cross 1 vector of observation. X is nothing but it is n cross p. Here each contain the p rows. So n cross p matrix including the p covariates. Beta is nothing but the p cross 1 vector of column vector of unknown parameters associated with these covariates. So in the model, what happened when I am saying that number of parameters, that means number of variables associated in the model. And E is nothing but, here it is a y cap minus x beta, it is not y. E is equal to y cap minus x beta, it is n cross 1 column vector of residuals. So as I was talking about how this particular originated. So as I say that Gauss and Legendre has given the concept of a classical theory of least square. So we will start from that. In Legendre in 1805 first proposed the estimating of beta by minimizing the quantity E transpose E. We call them as a residual sum of square. So how it is minimized? We know that just take the derivative with respect to parameters in the EI and equate it to 0, and then second derivative is a greater than 0. We say that beta cap is actually minimizing the quantity. Further, he showed in 1821 the estimates of beta obtained from the least square criterion having a minimum variance in the class of unbiased estimate, and that is how it is said to be a best linear unbiased estimator. Classical linear models are rooted in astronomy to study a solar system. So where this classical linear models arise, it is the arise from the study of solar system. It is coming from astronomy. There is a difference between the astrology and astronomy. So astrology means we call them as a Jyotish Shastra, and astronomy it is kind of a Khabul Shastra, where we try to study about the galaxy and there is a movement of the galaxy. Then what is the impact of the one planet on the another planet, gravitational force and other things. So that everything is studied in the astronomy. And in fact, Legender and Bose did many experiments on the solar system via telescope. And then whatever the data they have captured, they have identified the errors in the data of measurement. And then that is how the Bose has given the Gaussian approach to model the such error. The development of the theory of experimental design gave a new stimulus to linear models and very much associated with R. A. Fisher and his co-worker. We know that the concept of the design of experiment was given by the Professor R. A. Fisher, and that is how the Professor Fisher is known as the father of design of experiment. And he has started this whole experiment in the agriculture science. Fisher stressed the value of factorial experiment in which many experimental factors were applied simultaneously. So we know that there is a classical design and there is a factorial experiment. In classical design, you can have a one factor at a time, but in a factorial experiment, you can have a several factor at a same point of a time. Factorial design increase information per experimental unit, and the analysis lead to factorial models in which the yield were correct, considered as expressible as the sum of effect due to factor acting one at a time. That means in a factorial experiment, you have seen if there is a main effect and there is a interaction effect. So main effect means it is nothing but the impact of a factor at a time, and it will observe through the yield. Or and if you have a two-factor interaction, so that means a two-factor at a time, and so on. These factorial models are an important component of generalized linear models. So earlier, we have to study in a linear models. You have seen that if y and x both are quantitative in nature, you can apply the either linear models and linear regression analysis. But if your y is a quantitative and x is a qualitative, you can apply the design model. And if you are looking the factors more than one factor at a time, then you are using the another way of looking at the data by modeling. That is the concept of factorial experiment, where factors are considered in the either whether they are at the low level or the high level. So that factors are categorical. But generalized linear models also capture the same thing. In linear regression analysis, you cannot apply the when response is quantitative but effect is qualitative. There you have to go for the either design model or the factorial model. But generalized linear models also capture the same thing. As a single models, you can study the regression analysis, you can do the design models and everything in the generalized linear models. So as I say that when you talk about the factorial model, they are often called analysis of variance models and compared with the regression model for the observed data where we have a continuous covariance. An outline of generalized linear models or the process of model fitting. Earlier we have seen that is the one approach of the model fitting. Here there is another way of the model fitting which is given by the Box and Jenkins in 1976. So this models, Box and Jenkins has given the concept of the model fitting in the time series approach, and in the same approach we can also fit the models of generalized linear models. So Box and Jenkins has given the three important steps of model fitting in the generalized linear models. So we will use that approach for the fitting of the generalized linear models. So what is that? First approach is the model selection. First approach is a model selection. So what will you do in the model selection? Models that we select to fit the data will usually be chosen from a particular class. And this class must be broadly relevant to the kind of the data we have if the model fitting process is to be useful. So that means whenever you select the models, it should be coming from a wider class and it's also supported by the data. For example, we are selecting the linear models. So linear model, it is a class of the models, from that we select the model. But if the relation between the y and x is a curve in nature, collinear, and if we apply the simple linear, then perhaps we are making the mistake. So we have to select the class of the models, or we have to select the models from a specific class which is also relevant to the data. That means if the relation between y and x is a linear, then we have to talk about the linear model. If it is a non-linear regression, then we have to talk about the non-linear model, something like that. An important characteristics of generalized linear model is that they assume independence, or at least uncorrelated observation. So when we talk about the generalized linear models, I say that there are two properties are very important. First is a uncorrelatedness or the stochastic independent, and second one is the second order property, that is the variance is a function of mean. So when you fit the generalized linear models, you have to see that whether these two assumptions are verified. If yes, you can go for. For example, data showing the autoregressive of time series are excluded. Why it is excluded? We cannot fit the generalized linear models with the time series data. Why? Because in the time series data, we cannot say that data are independent. The current observation is a function of previous observation. If I wish to invest the money into the stock market, what is the price of today's price of this specific stock? It depends on the yesterday's price. Okay, so that means when I have a time series data, I cannot apply the generalized linear models. Why? Because it has the violate the assumption of the stochastic independence. This assumption of independence is that characteristics of linear models of a classical linear regression analysis and is carries over to the wider class of a generalized linear model. So stochastic independence is the basic assumption of a classical linear regression, and we are developing the generalized linear model as a wider class of a classical linear regression model. So we have to continue with the same assumption. It means if your data is from a time series, can we use generalized linear models? Then the answer is no. Why no? Because we are violating the property of stochastic independence. So while selecting the models, you have to see the nature of the data. Whatever the models we have selected, whether this model is supported by the data. We say that we will apply the generalized linear model, but data does not support it. Why? Because data are correlated, it is not independent. A second assumption about the error structure is that there is a single error term in the model. So earlier we said that if there are more than one error term, we cannot use. We just exclude, for instance, model for the analysis of design of experiment of kind giving rise to more than one errors. Simplest example is a split plot design with its two error term associated between the main plot and within plot comparison. So as I said in the earlier discussion, we cannot apply the generalized linear models when there are two error terms arises. Kind of example of a split plot design, where we have a one error from the main plot and another is from the subplot. So you have to understand the nature of the data. It is not like that I know the generalized linear models, I know the software, let me apply. No. First, we have to see that are we in that position to apply? Is generalized linear model supported by the data? Are we in that position to see that this data satisfy the basic assumption of a generalized linear model? If yes, then we can proceed. The restrictiveness of these two error assumption is in practice somewhat less than they might appear in the first sight. Sometimes what happens, we cannot realize these are easily we can get it. For example, with the multi-way tables of account of non-independence may arise because marginal total needs to be fixed in the analysis. So if you remember the cross-tabulation study you have studied in the second semester of BSc, and we have seen that is there any association between two attributes or not, and that has been assessed by the chi-square contingency table, and if the hypothesis is rejected through p-value, then we say that there is an association between two attributes, because null hypothesis what that the attributes are independent, or there is no association, statistical association between the two attributes. But do you say that they variables are independent or this? The non-independence arise because marginal totals need to be fixed. So either you have to fix the row total or you have to fix the column total. That means somewhere you are making the restriction. Getting my point? Similarly, within group analysis can ignore the correlation induced by the grouping factor in a nuisance classification, whose effects have to be eliminated before the effect of other factors can be estimated. So here you can talk about the split plot experiment. There are two types of errors. So if you wish to apply this, the first you have to remove the impact of the one nuisance factor. Here the nuisance factor is the main plot. Main plot again you have within plot. So you have to control the impact of that nuisance factor. The choice of scale of measurement is an impact aspect of a model selection. Now the question is, what do you mean by the good scale? In classical linear model, a good scale has to combine constant variance and approximately normality of errors with additive systematic effect. So when you say that good scale means it has the constant variance, we call them the stabilization of the variance, then the scale is a good. There is not much variation in the information, and it has the additivity of the systematic effect and having a normality assumption. Now there is of course no priori necessity that the scale with such desirable property should exist, and it is not difficult to imagine cases where it will not. So here you say that we should have an additivity effect, but that is not always the feasible. How? So let us understand this example. For example, the analysis of counts where the error structure is well approximated by the Poisson distribution, and the systematic effect of some classifying factors are multiplicative in nature. So we know that then the response is a count having a Poisson distribution, and if you develop a model, then the sum factors having a multiplicative effect. We do not have a additive effect. And further, if you look at the distribution of y, it is a Poisson, it is not a normal. Then what we do? Then we take the sum transformation. If we make the square root transformation of y, it will give the constant variance. Because as we say that when you say that the scale of the distribution or the scale of the data is very important. So what do you mean by the good scale? Which having the constant variance or stabilized variance, having the additivity effect, and third one having a normal errors. So if you have the y having a count, having a Poisson distribution, if you take the square root, then it has the constant variance. But it does not having a normality. And if you look for the normality, you have to take the transformation to third of y. Y raised to 2 by 3 will give the approximately normal. And because the effect are multiplicative, then it is saying that instead of the y, you have to take the log y. Because we know that the log a b is equal to log a plus log b. So that the multiplicative effect is converted into the additive effect. So it is not the easy to get the all the best scale. Sometimes you have to make a transformation to get the better scale. The extension of classical linear models to generalized linear models largely remove the scaling problem. So if you use the generalized linear models, then it is removing the maximum impact of the scaling problem. Normality and constant variance assumptions are no longer requirement of error component, while additivity or systematic effect can be specified to hold a transform scale if necessary. So here we are not looking for the whether the distribution is normal, whether it has the constant variance or not. When you apply the generalized linear models, we are not focusing on this because generalized linear models itself taking care of normality and constant variance. And if we are interested in additive effect, then of course we require to have some transform scale that we can do. There remains a major problem in the model selection. Now the question is that how to select the models. When I am saying that how to select the models means I wish to select the value of x1, x2, xp covariant so that I can have the best estimate of the y. That means I am trying to identify the systematic part, best systematic part. There is a large literature on this problem in a classical linear regression model. We are given a number of possible covariates x1, x2, xp, and it required to find a subset of this, which is some sense optimum or constructing as a set of fitted value mu cap equal to beta j xj. So if you remember in this regression analysis, we say that expected value of y is equal to x beta, and if it is a multiple linear regression, then it is nothing but the beta 1 x1 plus beta 2 x2 plus beta p xp. And if you find out its estimate, then beta is substituted by the beta j. So mu cap is nothing but the sum over j beta j xj. So that means there are p variables are there, and we wish to obtain the best estimate of this mean, because ultimately we are interested in regression, we are interested in the y cap. And what is the y cap? It is the estimate of expected value of y. And what is the expected value of y in the regression? It is a beta 0 plus beta 1 x. So when I am writing the y cap, I am saying that beta 0 cap plus beta 1 cap x. So ultimately, in the model, we always interested to find out the expected value of the response. And if y having a normal with mean mu and variance sigma square, then expected value of y is a mu and the estimate is a mu cap. But how to obtain this? So this estimate is obtained in a such a way that the parsimony of the model's criteria should be satisfied. The strategy you have to propose is that there is a balance to be struck between the improvement of the goodness of fit in the data obtained by the adding extra term to the model and extra increased complexity introduced by the such addition. So as we discussed, as we add more and more variables, what happen? What happen? Model become better and better. But when you add more variables, what happen? You are adding the extra complexity by variables. So that is how you require the balance between the complexity and the model fitting. So this is all about the first part of the model selection. It is the first steps under the on the line of the box and gen scheme. And then the second step we will discuss about the estimation. Once the model is decided, you have to go for the estimation part, and then there is a third part is a prediction part. So there are three steps under the line of a box and gen scheme. So that part we will see tomorrow. So what we have seen, anyone can narrate in a few minutes. Okay, let me explain. When we fit the generalized linear models, we should always look the nature of the data. Second part is that once the nature of the data is in our hand, we have to see that whether the model is linear, non-linear, whether it satisfies the basic assumption of the generalized linear models. What are the generalized linear basic assumptions? One is independence. That means you cannot deal with the time series data or the data where more than one kind of errors arises. Second one is second one is the variance
Variance
is a function of a mean.
frequency.
So we should go for that. Variance is a function of mean.
Hmm.
So in that way, you identify the nature of the data and go for the generalized linear models. But as I say that modeling is a art as well as the science. You have to apply the basic principles of science and apply your own experience while develop a model. Once you look at the data carefully, you identify the patterns in the data. To identify the patterns in the data means to identify the best value of the parameters. And when you say that the best value of parameters, it means it satisfies the sum bestness criterion, like in the classical theory of least square. We say that it should minimize the residual sum of square to obtain the best estimate of parameters. Once the model is fitted, we try to see that whether the model is really good or not. So we can apply the goodness of fit criterion. But again, here the thing is that when we say that when we say model is good, when we say that the model value is very close to observed value. So when you say that model value is very close to observed value, the first impression in our mind that let us add more and more variables in our model so that we can have the best estimate of the response. But when we add more and more variables, what happens? By adding variables, we are adding the complexity, and therefore models become more and more complex. Our approach is Here our approach is to obtain the best model which has minimum complexity. Getting my point?
Yes, sir.
So in that way, we have to go for the model. And once the model is with us and we satisfy this goodness of fit criterion, we can use for the fitting of the model. Sorry, we can use it for the prediction of the response. So this is one criteria. Second criterion of model fitting is suggested by the Box and Jenkins. So in the box and Jenkins, first we have to go for the model selection. Then once the model is selected, we have to go for the estimate of the models. And then third, we can go for the prediction of a model. And in model selection, we have to select the model which is a some member of a wider class and which supported by the data and having the less complexity. I think today we have seen that. We have also discussed about this some nomenclatures. Tomorrow we will go for these two other steps of the model fittings on the line of a box and Jenkins. And then we will go to the small mathematics as the response in the generalized linear models is a member of the exponential family. So what is the exponential family? What are the basic things we require while fitting of a generalized linear model? So that we will see tomorrow. Today's numbers are up to, I think it reach up to 45. So tell your friends to attend the classes. However, I have uploaded the earlier two lectures on my YouTube channel. You just search Dharmesh Rai Kundalia. You can get the earlier 2 days lectures. Okay. And I will upload the same on the YouTube again so that if you wish, you can get the recorded lectures. Okay. Any questions so far? So seems no questions. So thank you very much for attending the session. Take care. We'll meet tomorrow at again 10:45.